students, welcome to the new session for the chapter Haloalkanes and Haloarenes. In the previous class, we have started the preparation of haloalkanes. In that first, we have started the preparation from hydrocarbons. We have seen preparation from alkanes by free radical halogenation method. Okay, now I already told you in the previous class from hydrocarbons we can prepare from alkanes, that we have seen in detail in the last session. Today we are going to see in this session, okay, how are they prepared from alkenes. Okay, how are they prepared from alkenes. Now alkenes, you people know, okay, alkenes means they definitely will have a double bond. That is the reason we are calling it as an alkene. Okay, now alkenes usually undergo which reactions? Electrophilic addition reactions. Now whenever you have an unsaturation, which kind of reactions they usually undergo? They undergo addition reactions. They undergo, because any molecule doesn't want to be so unsaturated, so it will try to reduce its unsaturation. So to remove the unsaturation, what do? We add something to the double bond. Now we add something to the double bond. So here, to make alkene to a haloalkene, I will either add X2 halogen or I will add HX. Halogens, I can add halogens which we call as halogenation reactions. We can add HX which we call it as hydrohalogenation reactions. And both the reactions are which reactions? Electrophilic addition reactions, the most common reactions shown by alkenes. Now alkenes also show allylic substitution reactions. Okay, alkenes also show allylic substitution reactions forming haloalkanes. Now first, this is a very big part. Okay, this is a very big part because this addition of HX involves many rules and mechanisms. Okay, so what we will do is first we will finish addition of halogens. So what is the first method we are doing here? We are doing addition of halogens. Okay, here when I say X2, I mean halogens, and especially which halogens I am talking about here? I am talking about chlorine and bromine, because I already mentioned you in the previous session, fluorination we usually don't do because it is explosive, and I told iodination is very slow rate of reaction, so that we are not considering. So when I say addition of halogens here, I mean Cl2 or Br2. Now addition of halogens to alkene. Okay, now let us do addition of halogens to alkene. As I already mentioned, what do you call this process as? What do I call this reaction as? I call this reaction as halogenation reaction, and I already told you this reaction is your electrophilic addition reaction. This reaction is your electrophilic addition reaction. Now if you go into the halogenation process, okay, let us take an alkene, CH3 CH double bond CH2. I have taken propane. Okay, I have taken propane. Now here, okay, what should I do here? I can add Cl2. Okay, now always remember here, whenever you are doing halogenation, we usually prefer some solvents. Okay, so what are the solvents I prefer here? I prefer inert solvents. Okay, I prefer inert solvents, or I can also say, okay, I prefer less polar solvents. Okay, I prefer less polar solvents. I already explained you many times that, okay, we usually do organic reactions in less polar solvents but not high polar solvents. Now here when I say less polar solvents, here my solvents will be CCl4, tetrachloromethane, okay, CHCl3, trichloromethane, CHCl2, dichloromethane. So halogenation reactions are usually done with less polar solvents like tetrachloromethane, trichloromethane and dichloromethane. Now here I have taken my propene. I will take any solvent of the choice which we have, 3 of them. Okay, CCl4. Then what will happen? Okay, your halogen gets added here, CHCl and CH2Cl. Okay, so chlorine gets added onto the double bond, and you get what? Okay, if you see, I told you in the introduction classes only, if the halogen atoms are present on the adjacent carbon atoms, what kind of halide should I call them as? Now I can write here only addition of halogens to alkenes give which kind of halides to me? Give which kind of halides? I call them as vicinal dihalides. When I was doing introduction part only, I have explained you what do you mean by geminal dihalides and vicinal dihalides. When both the halogen atoms are present on the same carbon atom, I call them as geminal dihalides. When the halogen atoms are present on adjacent carbons, I call them as vicinal dihalide. Now, if you can name it now. IUPAC naming 1, 2, 3. Numbering will start from here. So, what is the name here? 1, 2 dichloro. 1, 2 dichloro-propane. Okay, 1, 2 dichloro-propane. Now here I can try bromination to here, CH3, CH double bond, CH3. Okay, this is what is the name of this compound? This is your 2-butene. Okay, this is your 2-butene. I can do bromination here. Okay, I can take any other solvent now. I'll take dichloromethane, CH2Cl2. Okay, now bromine gets added onto the double bond. So what do I get here? CH, okay, CH, Br, CH, Br, CH3. Again, I got my vicinal dihalide. What will be the name from this? I can number from either sides because it is a symmetrical molecule. So 1, 2, 3, 4. So what will be the name? 2, 3 dibromobutane. Okay, 2, 3 dibromobutane. What it will come as? 2, 3 dibromobutane. Okay, now I'll tell you a very important the thing here. If you see bromine water, okay, if you take bromine water, I'll write it here. Okay, if you take bromine water, okay, you people know bromine is a nonmetal whose natural state or the state, okay, whose natural state is what? Liquid. Bromine exists in which state? It exists in liquid state. Okay, and bromine is, okay, the color of bromine is red in color. Okay, the color of bromine is red in color. Okay, now when you treat your alkene which has unsaturation with bromine, okay, when bromine reacts with alkene, bromine, okay, what will happen? If bromine, if it doesn't react, what is its original color? It is red. Now when you do this reaction, bromine reacts with alkene, so what will happen? Bromine loses its red color. Okay, bromine loses its red color. This we call it as test for unsaturation. So this reaction, okay, this reaction can be used as test for unsaturation. This reaction can be used as test for unsaturation. How can it be used as test for unsaturation? Okay, if unsaturation is present, okay, if unsaturation is present, okay, if unsaturation is present, what will happen if unsaturation is present? Bromine decolorizes. Okay, what happens if unsaturation is present? Okay, bromine decolorizes. If in the molecule, okay, unsaturation is present, then bromine gets added onto this unsaturation. If unsaturation is not present, bromine will not get added onto this double bond, then bromine doesn't react. So bromine will still remain in the red color. If bromine is getting decolorized, means what? Bromine has got added onto a double bond. That is the reason if unsaturation is present, bromine decolorizes. So when I say bromine decolorizes, what will be, what is the color change? It becomes red to colorless. If in the compound unsaturation is not present, okay, bromine retains the color. Okay, if unsaturation, this is one point, and the next point is if unsaturation is absent. Okay, if unsaturation is not present, you can write, if unsaturation is not present, bromine retains color. Okay, if unsaturation is not present, okay, bromine retains color. Okay, if unsaturation is not present, bromine retains color. If unsaturation is present, bromine decolorizes. Clear? From red to colorless. Bromine decolorizes from red to colorless. If unsaturation is not present, bromine retains color. That is the reason this reaction of alkenes with bromine can be considered as test for unsaturation. You can't do it with chlorine because chlorine as such doesn't have any characteristic color. And bromine is a colorless gas. Okay. Okay, so hopefully you understood the addition of halogens onto alkene. It is an electrophilic addition reaction. It is an electrophilic addition reaction. What does addition of halogens onto alkene give? It gives vicinal dihalides. We have done the reaction with chlorine, we have done the reaction with bromine, and I have shown you how to do the addition reactions. And one point to remember here, we use less polar solvents like tetrachloromethane, trichloromethane, and dichloromethane. And okay, when the reaction happens with bromine, or when the alkene reacts with bromine, it decolorizes. That is the reason this we can use as the test for unsaturation. Now we will go to the second part, addition of HX, which is probably the most important part, and questions keep on coming from that part. So next let us see addition of hydrogen halides with the process we call it as what? Hydrohalogenation of alkenes to form haloalkanes. So now let us do that. Now let us do the addition of HX. Okay. Now when we do the addition of HX, which is your hydrohalogenation, because we are adding hydrogen and halogen, we call it as hydrohalogenation, and it is an electrophilic addition reaction. Now you will clearly see why it is an electrophilic addition reaction. Let me take an alkene to explain you this thing very properly for you people. Now when we talk about alkenes, now here when we talk about addition of HX onto alkenes, we will majorly talk about two rules, Markovnikov rule and anti-Markovnikov rule. Now, when I take an unsymmetric alkene, for example, I have taken CH3, CH, double bond CH2. This is my unsymmetric alkene. It is not symmetrical. You can easily make out it is an unsymmetric alkene. It is an unsymmetric alkene. Now, to this unsymmetric alkene, I have to do addition of hydrogen halides. Okay, I need to do the addition of hydrogen halides. Now when I do the addition of hydrogen halides, I usually do it using two rules. Okay, the one rule is Markovnikov rule. Okay, other rule is anti-Markovnikov rule. Okay, now when we talk about these two rules, why are these two rules used? These two rules are used to decide the product formed by the addition of HX to an unsymmetrical alkene. Why not symmetrical? In symmetrical, both the double bonded carbons are same, so any side you add it is fine. Anyways, I'll show you that also. But first let us try to understand unsymmetric alkene. Now I need to do addition of HX to the double bond. Addition of HX to the double bond. Now if you do the addition, if you do the addition according to Markovnikov rule, what does Markovnikov rule say? What does Markovnikov rule say? Negative part of reagent. What is the reagent I have taken here? HX. Now if you see here, H will be the positive part of the reagent, halogen will be the negative part of the reagent. I am not saying H plus is cation, X minus is anion, because we very well know here the bond existing is covalent bond, and I cannot talk about literal cation and anion. But if you compare, I told you in the previous classes too, this is a polar covalent bond, so one will have partial negative charge and one other will have a partial positive charge. So this I am just taking it as a positive electrophilic part of the reagent, and this I am taking it as a negative nucleophilic part of the reagent. Okay, you know, in a reagent, the positive part is called as electrophile and negative part is called as nucleophile. Now negative part of the reagent, negative part of reagent, sometimes we also call it as addendum. Addendum is nothing but the reagent. Negative part of reagent is added onto the carbon having less number of hydrogen atoms. Clear? Negative part of reagent is added to the carbon is added to the double bonded carbon. So let us add one more word, added to the double bonded carbon. Because we are only worried about this double bonded carbon, because my addition takes place only at the double bond. So I am worried only about the double bonded carbons. Now if you see Markovnikov rule, negative part of reagent or addendum, negative part of the reagent or addendum is added to the double bonded carbon, having less number of hydrogen atoms. So where does the negative part of the reagent go and get added according to Markovnikov rule? It will go and get added to the carbon having less number of hydrogen atoms. Now if we are doing the addition of this, what is the name of this compound? It is your propene or 1-propene. Now if I do the addition of HX onto propene, using Markovnikov rule, what should be my product? CH3 CH double bond CH2 plus HX, plus HX. Now the negative part of the reagent gets added onto the carbon having less number of hydrogen atoms. So here it will get added to this carbon. So this will be my product according to Markovnikov Rule. Now, when we come to the anti-Markovnikov rule, okay, when we come to the anti-Markovnikov rule, what does this rule say? And one thing you people need to remember here, anti-Markovnikov rule is what? See, now when I'm talking about Markovnikov rule, it is when Hx is equal to HCl HBr. Okay, Hx is equal to HCl HBr. Now, anti-Markovnikov rule we only talk when Hx is equal to HBr. Okay, that only this is not sufficient. Hx is equal to HBr. Okay, now what? One more condition, Hx should be HBr. That is the first condition. Okay, what is the other condition? In presence of, let me remove this bracket to avoid confusion. Okay, in presence of a peroxide. Okay, in presence of a peroxide. Okay, what is the, okay, here it should be Hx. Okay, Hx should be what? HBr. And if only HBr is there, that is not sufficient. If only HBr is there, then it will go to Markovnikov rule only. What is the other condition that should be satisfied? Hydrogen halide should be HBr and it should be in the presence of a peroxide. Okay, it should be in the presence of a peroxide. One more thing I want to tell you, Markovnikov rule involves electrophilic addition reaction. Okay, Markovnikov rule goes through electrophilic addition reaction, whereas your anti-Markovnikov rule, okay, whereas your anti-Markovnikov rule goes through free radical addition reaction. Okay, free radical addition reaction. So be very careful with this. Okay, be very careful with this, because if it is through Markovnikov rule, it will go through electrophilic addition reaction. If it is through anti-Markovnikov rule, it will go through free radical addition reaction. So the mechanism for, because we already told it is an electrophilic addition reaction, don't impart it to anti-Markovnikov rule also. Okay, when it comes to anti-Markovnikov rule, it is your free radical addition reaction. Okay, so what is anti-Markovnikov rule? And I told you the condition and the mechanism. Condition is this and the mechanism is this. Okay, so let us see the statement. Negative part of the reagent, negative part of the reagent, okay, negative part of the reagent is added to carbon, okay, is added to, again let me write double bond, is added to double bonded carbon, is added to double bonded carbon. I'll just write the contrast of this. Okay, is added to double bonded carbon having more number of hydrogen atoms. Okay, negative part of reagent is added to double bonded carbon having more number of hydrogen atoms. Okay, negative part of the reagent is added to double bonded carbon having more number of hydrogen atoms. Now if we do, see, in the previous case, negative part was getting added to the carbon having less number of hydrogen atoms if it is through Markovnikov rule, and I told you halogen can be HCl HBr. Okay, here when we go to anti-Markovnikov rule, the negative part of the reagent will get added to the carbon having more number of hydrogen atoms. Now if I do the addition of HBr in the presence of peroxide, okay, to propane, what will be the product? Let us see. Okay, CH3, CH, double bond CH2. I told you it should definitely be HBr. Now it should be in the presence of what? Peroxide. Okay, it should be in the presence of what? Now whenever I say it is a free radical addition reaction, you should always have the presence of sunlight. Okay, or UV light. Okay, always have the presence of sunlight or UV light. Here if you see the most famous peroxide that is used is your benzoyl peroxide. Okay, now here you can write what is the, which peroxide I usually use here? Benzoyl peroxide. Okay, benzoyl peroxide. The most commonly used peroxide is benzoyl peroxide. Okay, benzoyl peroxide in the presence of HNU, sunlight or UV radiation, because usually free radical mechanisms should be triggered by either heat or light. So you can take that also here. Now how will the addition happen? Negative part of the reagent will go and attack on the carbon having more number of hydrogen atoms. So what will be the product here? CH3, CH2, CH2Br. Okay, CH2Br. Okay, here I didn't specify halogen here. Here I didn't specify halogen because it can be HCl or HBr. So I have just written it as X here, and in the product also I wrote X. Here it can't be just X because we have lot of specificity here, because it should be HBr in the presence of the peroxide. So I can directly write it to be a bromine. Okay, now I can, okay, now these are I got two different products. I got two different products. You can do the react. If you do the reaction with HBr in the absence of peroxide, you will get this product. If you do the reaction with HBr in the presence of peroxide, you will get a different product. Now, the point comes here. The point comes here. Is it fine if we, in the exam, if any alkene comes regarding the addition of HX, hydrohalogenation, is it okay if we by heart the Markovnikov rule and write the no final product of the reaction? Is it fine if I by heart? Is it enough if I by heart this? Will I be able to solve all the questions with 100% accuracy? Definitely no. Because, okay, see, these rules definitely help. But if I say Markovnikov rule has been given, Markovnikov rule has not been given just like that. This rule, whatever Markovnikov rule I have written here, it has been framed based on a mechanism. Okay, based on a mechanism. Now, when you observe the mechanism involved here, then you will understand what made Markovnikov to frame this particular rule. Now, this mechanism as such now is not needed for us to answer any question. If you know this, if you have an idea how it works, it is enough, because the mechanism is supposed to be done in grade 11 in hydrocarbons chapter, but not here. But we should definitely be looking into the mechanism which led to Markovnikov rule, because he didn't give rule just like that. He would have done some work behind it. He would have observed the mechanism. Okay, when HCl and HBr are added to the alkene, and then only he has come to the rule. Now, it is very important for us to answer all the reactions with 100% perfection. For that, you should be knowing the mechanism of this reaction. Okay, now let us see the mechanism of the reaction. Now, let us see the mechanism for Markovnikov addition. Okay, so we have taken propene, and this is my double bond part. Okay, I will only focus on double bonded carbons. Now, if you see here, we are adding what? HX. We people know this is the positive part and this is the negative part. Now, if you observe this double bonded carbons, okay, I have this unsaturation over here. Now what exactly happens is, now we will keep the statement of Markovnikov addition aside, because we will try to understand it without that rule in mind, because that rule came from the mechanism. So let us understand a mechanism with a fresh mind. Okay, now if you take a double bonded carbon, in grade 11 you have studied about electromeric effect. Okay, you have studied about electromeric effect. So there is every possibility this double bond, okay, may move, okay, under the influence of a reagent. There is every possibility the double bond can the double bonded, the pi electron cloud, the double bond can move either onto this carbon or can move either onto this carbon. This I will take it as path A, and this I will take it as path B. Okay, when a reagent is approaching, because it is a double bonded carbon, it has unsaturation. The pi bond, okay, double bond is a pi bond. Okay, the pi bonded electrons, okay, can move either to this carbon or can move either to this carbon. Now imagine if it is following path A. Okay, imagine if it is following path A. Okay, what will happen if it is following path A? Okay, I will write it like this for your better understanding. Okay, imagine if it is following path A. Okay, if it is following path A, then what will happen? The electrons will get shifted here. Okay, the electrons will get shifted here. So this will be the negative part and this will become the positive part. Now when the electrons get shifted here, okay, I will write and show. If it is following path A, okay, if it is following path A, now this part will get a negative charge and this part will get a positive charge. Am I right? If it is following path A, the pi bonded electrons are transferred to this carbon. So this carbon will get a negative charge and this carbon will get a positive charge. Now what do you see here? You see a positive part and you see a negative part. So positive part will go and attack on the negative part. Negative part will go and attack on the positive part. So what do you get here now? Okay, CH3. Okay, CHX, CH3. Okay, CH3. Okay, this is what this is what happens. Now, okay, let me do it more step by step. Okay, now what happens? This electron cloud has moved here, so the hydrogen has attacked to this carbon. Okay, attacked to this carbon. Okay, now I'll write one more step here. See, this height, okay. We are talking about electrophilic addition. We are talking about electrophilic addition. When we are talking about electrophilic addition, the first attack we'll talk about is the electrophile. So this is my electrophile. I'll make it in more detail for you. This is the electrophile. Now this electrophile will go and attack on this CH2 minus. When this electrophile goes and attacks on this CH2 minus, it will become CH3. Am I right? Now this will become my secondary carbocation. Okay, this will become my secondary carbocation. First electrophile has attacked. Now what will I do? What is my other part which is my nucleophilic part? Now the nucleophilic part goes and attacks. Now the nucleophilic part obviously will attack on the positively charged carbon. So this is my product. Okay, now if the electron cloud or the pi electron gets, or the double bond is nothing but pi electrons only, if the pi electrons get transferred onto this carbon, if it is following path A, now why are they moving? Under the influence of the reagent. If the pi electron cloud is moving, that is the electromeric effect which you have studied in your grade 11. Due to electromeric effect, if the shift is happening onto this carbon, then this is what happens. Okay, electron cloud goes onto this carbon. Negative charge comes here because the electrons are going away from this carbon. Here I'll get my positive charge. Now I am doing electrophilic attack here. Now I can write here electrophilic attack. Okay, I can write here electrophilic attack. Now electrophilic attack happens. Now I am getting my secondary carbocation. Nucleophile attacks. Now I got my product. Okay, now what if it is going to path? Okay, what if it is going through path B? Okay, what if it is going through path B? But in path B, what is happening? Electrons are moving on to this carbon. So what will I get here? CH3, CH, negative charge. Okay, then this will get positive charge because electrons are going away from this carbon. This will get positive charge. Electrons are going towards this carbon, so this will get negative charge. Now what will I do? I will do the electrophilic attack. Electrophile is my positively charged H plus here. Electrophile will attack where? Electrophile will attack here. Okay. Okay, I hope this is clear for you. My electrophile will attack here on the negatively charged carbon. So here I will get CH3, CH2, CH2 plus. Now if you see here, which type of carbocation is this? Primary carbocation. If the positively charged carbon is attached to a single carbon, it is primary carbocation. If the positively charged carbon is attached to two other carbons, it is secondary carbocation. Now this is my primary carbocation. Okay, on to this, now my nucleophile will attack. Now what will I get here? CH3, CH2, CH2X. Okay, you got two different products. Okay, if imagining the path A, the product is this. Okay, imagining path B has happened, my product is this. Now how should I decide? How should I decide which is formed in major and which is formed in minor? How should I decide which is formed in major and which is formed in minor? I told you when I'm teaching alkanes mechanisms also that, okay, how do you decide which product is major? Whichever path passes through the most stable intermediate. Now if you see here, what is my intermediate here? Okay, if you see here, what is the intermediate? You see in this mechanism, the intermediate is your, okay, the intermediate is your, okay, carbocation. Now, so who will decide which product is major and which product is minor? The stability of carbocation. Now, secondary carbocation and primary carbocation, which is most stable carbocation? What is the stability order of carbocations? Okay, what is the stability order of carbocations? Okay, what is the stability order of carbocations? Tertiary carbocation is more stable than secondary, then it comes to your primary. The reason for this is hypoconjugation. Okay, the reason for this hypoconjugation. Wherever it can form more hypoconjugating structures, that will be the more stable carbocation. So if you compare these to the secondary carbocation, is more stable. So this path has the most stable intermediate. That is the reason I will consider this product to be major and I will take this product as my minor product. Okay, now if you observe the major and minor product, now see here, observe the major product, where is the negative part of the reagent attached to the carbon having less number of hydrogen atoms. Come to the path B, where is the negative part of the reagent attached to the carbon having more number of hydrogen atoms. Now did you understand how did Markovnikov frame that rule? From here only. After he found out rule, he didn't go to the mechanism. Once he found out the mechanism, then he gave the rule that the negative part of the reagent will attack onto the carbon having less number of hydrogen atoms, because it is proven by the mechanism, because the mechanism goes through a carbocation intermediate and the more stable carbocation will give you the more stable product. This is how Markovnikov has given Markovnikov rule for the formation of haloalkanes from alkenes by hydrohalogenation. Okay, so this is how you understand this, understand the mechanism. It is very important for you to understand this mechanism. Now, okay, now there is one more twist here. Okay, we know the mechanisms. Okay, we understood the mechanism. Through this mechanism, Markovnikov has given certain rule acceptable. But will this rule be blindly applied to all the alkenes? Then it is a definite no. Then it is a definite no. What is this twist again? I'll tell you what is a twist again. I told you this mechanism goes through carbocation, and we have to decide the product based on the stability of carbocation. Now sometimes you can't directly say that I got this carbocation, I'll attack here, because sometimes you can do the shifts and produce a more better carbocation. If I say like this, you won't understand. Let us take an example and see when is the rearrangement needed to decide. Now let us see an important concept called hydride shift or methyl shift. Now these shifts will decide the product in Markovnikov addition sometimes. When do they decide on all, we will see now. Okay, to make you understand, okay, why do hydride shift and methyl shift happen only in Markovnikov addition? Okay, because your Markovnikov addition, okay, happens through carbocation intermediate. Okay, carbocation intermediate. That is the reason we talk about hydride shift and methyl shift only here. Now, without explaining the shift, if I tell we can't apply it for anti-Markovnikov, you will not understand. So let us do this first. For example, usually children do this mistake here. They blindly by heart Markovnikov rule, and when they get a question on hydrohalogenation on alkenes, they write a wrong answer. Okay, the reason for that is, for example, take this compound CH3, CCH3, CH double bond CH2. This is my alkene. This is my alkene. Now, okay, you got this question in the exam. In the question they have given what? In the question they have given HBr. Okay, they didn't give any peroxide. So what you will do? You will do Markovnikov addition, and what you will write the answer? This is my positive part. This is my negative part. Negative part will go and attack on the carbon having less number of hydrogen atoms, and you will write the answer as CH3, CH, CH3, CHBr, CH3. This is how you will write the product according to Markovnikov rule, and you feel okay, Markovnikov rule is very standard rule. Definitely it is, but here if you feel this answer is right, no, then the answer is wrong. Why is the answer wrong? Okay, why is the answer wrong? To understand why is the answer wrong, let us quickly see the mechanism of this reaction. That is the reason you should be knowing the mechanisms of at least important organic reactions. Now if I try to write the mechanism for this, okay, CH3, okay, CH, CH3, CH double bond, now a double bond CH2. Now you people know this is a double bonded carbon. This is a double bonded carbon. I have my reagent. Okay, I have my reagent. Now carbocation will form. There is every possibility if electrons move to this side, I will get a secondary carbocation. If electrons move to this side, I will get a primary carbocation. Now this time I am not going in so much detail. You people know secondary carbocation is more stable, so I will be directly writing only secondary carbocation because I already taught you in the mechanism previously. So okay, if electrons shift towards this carbon, here I will get positive charge, so then it will become my secondary carbocation. Okay, if electrons shift to this side, this will get positive, then that will become my primary carbocation. Now from now we will write only the stable carbocation. Okay, so here if this happens, what will happen? I will get CH3, CH. Okay, let me write this like this. Okay, CH3, CH, CH3, CH, CH. Okay, CH3. So this is according to what we have studied till now. Okay, the migration will happen. Okay, what will happen now? I will get my secondary carbocation here. Next step is what? I have to attack my Br and I will get Br here. This is the expected one, right? This is the expected one. Okay, this is my secondary carbocation. In the two possibilities I had, okay, this was the stable one. So next step should be attack of Br minus. That is, if you do like that, you would have got this, definitely this answer. This is wrong. Why it is wrong, I will tell you. Now you see it. Okay, now you tell me the stability of carbocation. Most stable is tertiary, then secondary, then primary. Okay. Now, if you compare, okay, here what did you do? You compared between primary carbocation and secondary carbocation. When you compared between primary and secondary carbocation, you felt secondary carbocation is very stable because it's a proven fact through hyperconjugating structures. Now, I got a thought here. Tertiary is more stable than secondary. So let me see, can I do any rearrangement or can I do any shift so that I can get a tertiary carbocation here? Then I thought, okay, let me sometime throw the light on the carbon which is present beside this secondary carbon. If you see this, okay, what kind of carbon is this? Okay, tertiary carbon. What kind of carbon is this? Tertiary carbon. Now, on this carbon, I have hydrogen and I have methyl. Okay, if I shift one group from here to here, if I shift one group from here to here, then I get a tertiary carbocation here. I can either shift, see, H plus is when hydrogen is going without a bond. Okay, H minus is when hydrogen is leaving with a bond. Okay, when hydrogen is leaving with a bond, I call it as H minus. In the same way, if methyl is leaving with a bond, it is CH3 minus. It is CH3 minus. Now, I can either shift hydrogen with the bond or I can either shift methyl with the bond so that this carbon will get positive charge. Now, when this carbon gets positive charge, it will be my tertiary carbocation, which is more stable than my secondary carbocation. Now comes the comparison. Should I prefer hydride shift or methyl shift? Okay, now we will always prefer hydride shift over methyl shift. We will always prefer hydride shift over methyl shift. The reason is hydrogen is a lighter group. Okay, hydrogen is a very lighter group, so I prefer, okay, I prefer moving a lighter group. See, transferring a lighter group onto the next carbon is easy than transferring a bulkier group. So when you have competition between hydride shift and methyl shift, you will always do hydride shift. Now, if you don't have the option, even if this hydrogen is also methyl, okay, here I had a competition between hydride and methyl. Now, if you don't have the competition and you had methyl here, for some time I'll write and show. If you had methyl here, then there is nothing to decide. There is no competition only. Obviously, you will shift one of the methyls. Okay, obviously you will shift one of the methyls. Okay, but here that is not the case. I have a hydrogen and methyl, so you should have a clarity on what should be preferred over the other. So I will prefer hydride shift because it is a lighter group. Now what will I do? I will do hydride shift here. Okay, if two methyl groups are there, you will do methyl shift. Okay, now don't think that I will, okay, if two hydrogens are there, I will shift hydrogen. Then that is not the case. No? See, if you people are thinking, okay, if you people are thinking like this, okay, CH2, CH, CH3, CH3. Now, I can't shift hydrogen from here, no? In this case, I won't shift hydrogen from here. See, this has two hydrogens. Now, you people will think, I will shift hydrogen from here. Then what you will get? If you shift hydrogen from here, then you will get again your secondary carbocation only, no? Then again you will get your secondary carbocation only. So there is no point in doing that. So looking at the question, how should you understand that I should do a hydride shift or methyl shift here? Looking at the question, how should I get an idea to do a methyl shift or a hydride shift? Now if you see, this is my double bonded part. Okay, this is my double bonded part. Look at the carbon adjacent to this double bonded carbon. Okay, look at the carbon which is adjacent to the double bonded carbon. If this carbon is a tertiary carbon, okay, if this carbon is a tertiary carbon, then obviously it will have definitely one methyl group. So if you remove any one of these two groups, you can get a tertiary carbocation. That is how you identify. Just look at the carbon which is beside the double bonded carbon. If it is a tertiary carbon, then you can think about hydride shift or methyl shift. If one hydrogen and methyl are there, then go for hydride shift. If two methyl groups are there, obviously you shift one methyl. Okay, clear with that? Okay. Now when I do the hydride shift here, what will I get now? Okay, let me write it like this. Okay, after doing hydride shift, what is the product I get here? CH3, C positive charge, because hydride has got transferred here, this will become CH2, okay, CH3, okay. Now, okay, I did hydride transfer, so my methyl will still be there. Now this is what? This is my tertiary carbocation, which is more stable than my, okay, secondary carbocation. This is more stable. Now you understood why was this answer wrong. If you would have done here only the addition of Br minus onto this carbon, then your answer is wrong, because I had a possibility, of getting a more stable carbocation, so I should use the possibility because to get a stable carbocation intermediate. Now you do Br minus attack. Okay, now you attack Br minus. Now you get CH3, C, Br, CH3, CH3, CH3. So this will be your final answer. Okay, so the naming I am not doing because you people are very perfect with the naming process. Okay, so this will be your final answer. Okay, understood when to do, understood how to do. When hydrogen and methyl are there, do hydride shift. If both methyl groups are there, obviously you will do methyl shift only. How to understand if I have to do any shift? The carbon adjacent to double bonded carbon should be a tertiary carbon. Now I have written something here. Let us come to this part. Now why can't I talk about hydride shift and methyl shift if it is anti-Markovnikov addition, which is also called as peroxide effect, because we can do it in the presence of peroxide. Either you can take hydrogen peroxide or you can take benzoyl peroxide. We call it as peroxide effect. It is very famously called as Karash effect also. These three names you remember, it's better, because in exam if you use any other name, you should not be in any confusion. Okay, so what are the peroxides used? Mainly hydrogen peroxide and benzoyl peroxide, and as I already mentioned you, it is only used for HBr addition in the presence of peroxide. Now if you are thinking why not HCl, okay, why am I always specifically before that a very important point, why can't I talk about this this shift, hydride shift and methyl shift in anti-Markovnikov addition? Here I was talking about hydride shift and methyl shift because it is through a carbocation intermediate. I will talk about rearrangement. Here it is through free radical. Here the mechanism is what? Here the mechanism is your free radical addition mechanism. Here there is no point I talk about any rearrangement happening like that. Okay, it is free radical addition reaction, so no rearrangement like this will take place to get a better carbocation. That is the reason hydride shift and methyl shift is not applicable for anti-Markovnikov addition. So any question coming under anti-Markovnikov addition, you can simply follow the thing that if you see the condition is HBr in the presence of a peroxide, go and put the negative part of the reagent on the carbon having more number of hydrogen atoms. That's it. There is no point of any confusion here. Okay, now when we see why not HCl, okay, why I have been constantly telling it should be HBr in the presence of peroxide, why not HCl in the presence of peroxide? Okay, why not HCl in the presence of peroxide? There is a reason for this. Okay, the quality of a very good science student is always keep questioning the things. Okay, not on silly things, but wherever it is valid, you have to keep on questioning the things. Why not HCl in peroxide? The reason for here is, now when I told anti-Markovnikov mechanism, I told free radical. Now it is, if I take HBr bond and HCl bond, now you people know chlorine is more electronegative. Okay, chlorine is more electronegative compared to bromine. Bromine is less electronegative, because if you go down the group, the electronegative character increases. So bromine is comparatively less electronegative in the halogens. Now because it is less electronegative, the charge separation is not so big. Okay, the charge separation is not, so the polarity of the bond is less. Polarity of the bond is less. Okay, here what happens? Here polarity is less. Here polarity is less. Here what happens? Here polarity is more because chlorine is more electronegative. Now because the polarity is less, it is possible for me to break this bond and form free radicals H dot and Br dot. But when we come to HCl, if you see, the charge separation is more. Okay, the charge separation is more. The charge separation is more. That is the reason free radicals can't be produced. Okay, free radicals, okay, here it is less polar, so I can break it homolytically. Here it is, okay, here the polarity is less, so I can break the bond homolytically, okay, which will lead to free radicals. But when the polarity is so much, I can't talk about homolytic fission because electrons are more pulled towards chlorine. I can only talk about heterolytic fission, which will give me charged entities, electrophile and nucleophile. So free radicals not produced. Okay, here the free radicals are not produced. Here the free radicals are not produced. That is the reason I will not talk about any free radical mechanism if it is HCl. That is the reason anti-Markovnikov rule is not applicable for HCl in the presence of peroxide. Because of the more polarity of HCl bond, free radicals cannot be produced. Whereas in HBr, due to the less charge separation, there is possibility of production of free radicals, so they can show anti-Markovnikov addition. Okay, so this is all about your hydride shift, methyl shift, why it is only for Markovnikov rule and why it is not applicable for anti-Markovnikov rule. And one more very important concept we have seen, why not HCl in peroxide for anti-Markovnikov addition due to polarity. I told you the reason in very much detail. Okay, so we have seen addition of halogen, which is halogenation. We have seen addition of HF, which is hydrohalogenation. Now we are left with last preparation from alkenes, which is by allylic substitution, which is a very small concept. Let us do that now. Now let us see the last method of preparation of haloalkanes from alkenes, which is allylic substitution. In the initial classes, I already taught you what is allylic halide, what is vinylic halide. Now let me take propene here. Okay, let me take propene here. Now if to form, now it is a very common sense now. To form an allylic halide, I should do substitution at this carbon. Okay, I'll write and show you. For example, if I am taking Br2 at a temperature of 700 to 800 degrees Celsius, now bromine will get substituted on this carbon. It should be a very high temperature. Okay, it should be a very high temperature. Okay, because if it is not very high temperature, there is every possibility it will produce free radicals. Okay, now here I don't want free radical. Okay, that is the reason I will maintain a high temperature. Now what will happen? What do I get here? I get the substitution of bromine at the allylic position. Okay, so this is which halide? This is my allylic halide. This is my allylic halide. Clear? Okay, very important. Okay, is this the only way I can get this? No. Take an unsymmetric alkene like this. Now you can also use NBS. What is NBS? NBS is your N-bromosuccinimide. Okay, NBS is your N-bromosuccinimide. Okay, you can take NBS. Okay, and this happens in the presence of sunlight. Okay, you can do this in the presence of sunlight, or you can slide. Okay, it's better you use sunlight only, or you can go for UV light. You usually don't heat this. You will use sunlight or UV light. Now when I use N-bromosuccinimide, when I use N-bromosuccinimide in the presence of sunlight or UV light, the substitution happens at this position, forming an allylic halide. So because it is N-bromosuccinimide, there is only possibility of bromine coming here. CH double bond CH2. Here if you see, we are interfering with the double bond though. The double bond remains intact. Okay, the double bond remains intact, and the substitution happens at the allylic position. The substitution happens at which position? Allylic position. Because the substitution is happening at the allylic position, I call it as allylic substitutions. Okay, you can now if you are now let me take one more example. See, NBS, N-bromosuccinimide, can do only allylic bromination. It is only very particularly used for allylic bromination, and it is very much common sense because it has bromine. It can do only allylic bromine. Okay, allylic position, at allylic position it can only substitute bromine. Now you can take one more example. Okay, you can take any example here. Okay, now I will take Cl2 in the presence of 700 degrees to 800 degrees Celsius. Where is my allylic position here? Here. So my substitution will happen at the allylic position. So double bond will not be affected. That is the reason, if you see, if I don't take this 700 to 800 degrees Celsius, and if I take a normal condition, imagine I have not given these conditions, then what will happen? Halogenation will happen, and both the halogens will get added to the double bonded carbons. Is halogenation happening here? No. I am using the same bromine and same chlorine only. In the first process where I taught you addition of halogens, I told you halogens will go and get added onto the double bond. Here the halogens are not getting added onto the double bond. Okay, getting added onto the double bond. Instead, what is happening? They are going and doing substitution at the allylic position. That is mainly due to the temperature conditions I have provided here. That temperature conditions will control the process. Here my N-bromosuccinimide in the presence of sunlight or UV light will control the process and see that only allylic substitution is taking place here. Okay, this is see, NBS is pretty many times asked in the examination, so it's better you have an idea of allylic substitution, because they can ask allylic substitution. As usual, addition of HX is very important. So addition of halogens and allylic substitution also you should have an idea, because you never know from which part they ask questions. Okay, so this is all about the preparation of haloalkanes from alkenes by halogenation, by hydrohalogenation, and by allylic substitution. I taught everything in very much detail, and I try to cover all the important points which are needed for you for the examination, including the hydride shift and methyl shift. Hope you understood the session. Hope you loved the session. In the next session, I'll be teaching you the preparation of haloalkanes from alcohols and other named reactions for the methods of preparation of haloalkanes. Till then, keep watching our channel. Bye.